Hey guys, so let's talk about testing. Now I know that for software engineers, testing has always been something like going to the gym, something like we have our app and it's nice and we love it, but there's this thing that we need to do and we need to do it on a regular basis, but we don't really want to do it. We'll do it if we have to. Um, what I realized is that it doesn't have to be that way. Since vibe coding came about, testing is not that painful, it's not that difficult, it's not that time consuming. So I made this video, two parts. First part is the theory. That's the long part, stuff that you should know about testing, stuff that's good to refresh before a job interview, for example. And then the second part is practice, which is going to be short. It's just a few minutes, just to show you how easy testing is with Claude Code these days, and there's no reason you shouldn't have it. So let's get going.
How do you know the code written for you is good? This is the question everyone is asking right now. And it's not a rhetorical question. It deserves a real answer. Vibe coding is a rare phenomenon, a technology that is both genuinely new and already massively popular. That almost never happens, and that speed of adoption has created a backlash. The criticism comes from experienced engineers who have watched hype cycles before. Their argument is straightforward. If an AI writes the code, how do you know it works? How do you know it handles edge cases? How do you know it doesn't introduce subtle bugs that only surface under load or in production, or 6 months from now? These are not bad questions. They are exactly the right questions. The mistake is assuming there is no answer. The answer to how do you know AI-generated code is good is the same answer software engineering has given for decades. You don't trust code. You verify it. You test it. You prove it works by defining what works means and then mechanically checking that the code meets that definition. What's different now is that the same AI that writes the code can also write the verification, and that changes the economics of testing completely. Comprehensive testing, the kind that most teams know they should do but never have time for, becomes trivially fast to produce. The cost of doing it right drops to near zero. The excuses disappear. This video covers the theory, what testing actually is, why each layer exists, what traps to avoid, and how to think about testing as a senior engineer. Part 2 is the demo, building a full test suite across every layer using Claude Code in real time. Here's what we'll cover. First, the testing pyramid, 4 layers of confidence. Then mocks versus reality, why mocks lie in the container revolution. Anti-patterns and traps, including the ice cream cone. Gating versus monitoring, when each test runs and why. The paradigm shift, how AI changes everything. And in video 2, the demo, building a full test suite with Claude Code. Let's start with the testing pyramid. The testing pyramid is a model created by Mike Cohn in 2009 that visualizes the ideal distribution of tests in a software project. It's shaped like a pyramid for a reason, many fast, cheap tests at the base, and fewer slow, expensive tests at the top. Each layer catches a different class of bugs, and no single layer is sufficient on its own. This isn't arbitrary. It's shaped by economics. Unit tests are cheap, so you have many. E2E tests are expensive, so you have few. The pyramid is an investment strategy, not a rule of thumb. Here's a quick overview of all the layers. Unit tests verify individual functions in milliseconds, and you have hundreds to thousands of them. Integration tests check your code against real dependencies in seconds. Contract tests verify service boundary agreements. E2E tests cover complete user journeys but take minutes. And smoke tests are a tiny post-deployment sanity check. Let's dive into each one. Layer 1 unit tests. Unit tests verify the smallest meaningful unit of behavior in complete isolation. A unit is typically a function, a method, or a small class. You provide input X and assert that the output is Y. Nothing else is involved. No database, no network, no file system. They are the foundation of the pyramid, because they provide the fastest, most precise feedback available. When a unit test fails, you know exactly which function broke and exactly what about it is wrong. There is zero ambiguity. They're blazing fast. A suite of 2,000 tests runs in seconds. They serve as living documentation. They enable fearless refactoring, and they're cheap to write. No infrastructure needed. But unit tests have real weaknesses. They're completely blind to integration problems. You can have 100% unit test coverage in a system that doesn't work because the pieces connect incorrectly. They are prone to testing implementation rather than behavior, which is the single biggest trap in unit testing, and they can create a false sense of security. The senior take, the real skill with unit tests, is knowing what to test. Testing a getter is waste. Testing that your odds calculation correctly handles a 3-leg accumulator with 1 voided leg, that's where unit tests shine. The heuristic, if this function broke in production, would it cost money or hurt users? If yes, test it thoroughly. And the number one trap, if your test breaks every time you refactor, even though behavior hasn't changed, the test is testing how you do something, not what you do. Assert outcomes. Order status is paid, not. Save was called with this exact argument. For tools, in TypeScript and JavaScript, use Jest or Vitest with built-in mocking. In Java, Junit 5 with Mockito. In Python, PyTest with UnitTest.mock, and in .NET, XUnit with MoQ. Layer 2 integration test. Integration tests verify that 2 or more components work correctly together. The key word is boundary. You're testing the boundaries between your code and real external systems, databases, message brokers, caches, HTTP APIs. Your SQL query might have a syntax issue that a mock would never catch. Your Redis key might have a subtle encoding problem. Your event might serialize fine, but fail to deserialize on the consumer side. These are real production bugs that only surface when you test against real systems. Here's the critical distinction. Integration tests are inward-facing. They test your service's ability to work with its own dependencies. Your service owns the database. Your service owns the cache. You're testing your code against your infrastructure. This is the key difference from contract tests, which are outward-facing. On the strength side, integration tests catch an entire class of bugs that unit tests are structurally incapable of finding. They test real behavior, transactions, constraints, indexes, connection pooling. You get schema validation for free, and they provide much higher real-world confidence. On the weaknesses side, they're slower. Container startup adds seconds to minutes. They're more flaky by nature. They're harder to debug, and they require Docker in your CI environment. For tools, test containers is the modern standard. Also, Docker Compose, Supertest for HTTP testing, and Spring Boot test for Java. Layer 3 contract tests. Here's the scenario. Team A changes their API response from UserID, camel case, to user_ID, snake case. All their unit tests pass. All their integration tests pass. Their E2E environment happens to be stale. It deploys. Service B breaks. Users are affected. Contract tests catch this in the pipeline, before merge, before deployment. They verify the agreement between 2 independently deployed services, without requiring both to be running simultaneously. Here's how it works in practice. Step 1. Your team, the consumer, writes a contract. When I post to payments charged with this body, I expect back a response with these fields. Step 2. This contract is shared via a pact broker, which is a central registry. Step 3. The provider team runs the contract against their actual API in their CI pipeline. If the response doesn't match, their build fails. They find out before deploying. The key insight, in a monolith, the compiler catches interface mismatches. In microservices, there is no compiler across the network boundary. Contract tests are that compiler. Here's the analogy that makes it click. An integration test is like test driving a car to make sure the engine, transmission, and brakes work together. You own the whole car. You're testing your components. A contract test is like verifying that the fuel nozzle at the gas station fits your car's fuel port. You don't own the gas station. You don't need the gas station to be there during your test. You just need both sides to agree on the shape of the interface. PACT is the industry standard. It's open source, available on NPM as AutoPACT Foundation, PACT, and supports JavaScript, TypeScript, Java, Python, Go, Ruby, .NET, and more. Layer 4 end-to-end tests. E2E tests validate complete user journeys through the entire system. You're simulating what a real user does. Log in, browse, perform an action, verify the result. They exercise the entire stack: front-end, back-end, databases, authentication, third-party integrations. They provide the highest confidence. Does this system actually work for a real human? They catch what no other layer can: CSS bugs, auth flows, third-party integration failures, and they're directly tied to business value. Each test represents a critical user journey. Tools: Playwright, Cypress, and Selenium. But E2E tests have a critical weakness: flakiness. They're slow. Each test takes seconds to minutes. They're expensive, requiring full infrastructure. And they're inherently flaky because they depend on every layer of the stack. Any layer can cause a false failure. Here's the key insight. Once a team starts saying that test always fails, just rerun it, the entire test suite loses its authority. That's a worse outcome than having no E2E tests at all, because now you have a false sense of coverage. The senior take 10 to 20 curated tests maximum. If an E2E test isn't protecting a business-critical flow, delete it. It's just a maintenance burden. And a bonus layer: smoke tests. These are a tiny subset of E2E tests, typically 3 to 5, that answer one question. Did this deployment fundamentally break something? They run immediately after every deployment and complete in under 60 seconds. Does the login page load? Does the API respond 200? Is the database connected? If any of these fail, you roll back immediately. No questions asked. Now let's talk about one of the most important debates in modern testing: mocks versus reality. Mocks exist because of a fundamental tension in testing. You want to test your code in isolation, but your code doesn't live in isolation. It talks to databases, APIs, queues, and file systems. A mock replaces a real dependency with a fake one you control. The pros: mocks are blazing fast, no network calls, no I/O. They're deterministic. They never flake. They let you simulate exotic failures easily, like 500 errors and timeouts. And they enable parallel development before APIs even exist. The cons: mocks lie about real behavior. They don't enforce unique constraints. They don't validate auth tokens. They don't expire cache keys. They couple tests to implementation. They create maintenance whack-a-mole. And they mask real integration bugs. Works on my mocks is the testing equivalent of works on my machine. Let me emphasize this. A mock is your assumption about how a dependency behaves. If that assumption is wrong, your tests pass, but your code is broken. You're testing a fantasy, not reality. The modern approach: don't mock what you can containerize. Instead of faking a PostgreSQL response, spin up a real PostgreSQL instance in a Docker container. Instead of mocking Redis, run actual Redis. Libraries like test containers make this trivially easy. This is specifically an integration testing technique. Layer 2. Containers replace mocks at the integration boundary. You're not doing this at the unit test layer. That should be fast and isolated. And you're not doing this at E2E, where everything is already real. Container pros: truth over assumption, real transactions and constraints, schema validation for free, and no mock maintenance. Container cons: slower startup, resource heavier in CI, can't easily simulate exotic failures, and requires Docker. The best strategy is both. This is not a tribal war. It's about knowing which tool fits which problem. Use a container for your happy path with a real database. Use a mock when you need to simulate a 500 error or network timeout. Use a container for Redis TTL behavior. Use a mock for third-party services like Stripe that you can't containerize. And if it's your own PostgreSQL, test it for real. Use both strategically. Now let's talk about what not to do and why teams do it anyway. The ice cream cone anti-pattern. Take the testing pyramid and flip it upside down. Tons of E2E and manual tests at the top, some integration in the middle, and almost no unit tests at the base. Why does this happen? It feels intuitive. If I test the whole thing end to end, I'm covering everything, right? It's also the path of least resistance for teams without strong testing culture. Why it's catastrophic at scale, the feedback loop collapses. A developer changes one line and waits 45 minutes. Flakiness spirals. More E2E tests means more flakiness means more reruns means less trust. Debugging becomes archaeology across 6 services, and cost explodes because you need full environments for every PR. 6 booby traps to avoid. Trap 1, testing implementation, not behavior. Assert outcomes, not method calls. Trap 2, the 100% coverage trap. Coverage is a floor, not a goal. Trap 3, test suite entropy. Delete dead tests, question tests that never fail. Trap 4, shared mutable state between tests. Each test must own its own state. Trap 5, testing the framework. Trust Spring, trust Express, test your business logic. And Trap 6, the deadliest, flaky test normalization. When rerunning becomes normal, real failures get rerun too and shipped to production. Flaky tests must be fixed or quarantined, never tolerated. Act 5, gating versus monitoring. This is one of the most important operational concepts in modern testing. It separates senior engineers from junior ones. Gating means the test blocks something from progressing. A PR cannot merge. A deployment cannot proceed. If it's red, the process stops. Gating tests must be fast, reliable, and high signal. Monitoring means the test informs but does not block. It runs on a schedule, nightly or post-deployment, and alerts when something fails. Monitoring tests can be slower and more comprehensive. The mistake most teams make, dumping everything into the PR pipeline. Unit tests, integration tests, E2E tests, performance tests, all gating every PR. The result, 30-minute builds, constant flakiness, and developer rebellion. Here's how to assign each test layer to the right mechanism. Unit tests gate every PR. They're fast, reliable, precise. Integration tests gate merge to main. Reliable with containers, contract tests gate every PR. Fast, catches interface breaks early. E2E tests monitor with a nightly suite. Too slow and flaky for a PR gating. Smoke tests gate every deployment. Tiny, fast, high signal. Performance tests monitor weekly. They need stable baselines. The principle, gate with fast, reliable tests. Monitor with slow, comprehensive tests. Never gate with something flaky. Never relegate something fast and reliable to nightly only. Act 6, the paradigm shift. Before AI, there was a well-known trade-off. Thoroughness versus speed. Writing comprehensive tests at every layer took as long as writing the code itself, sometimes longer. Most teams, under deadline pressure, rationally chose to undertest. They skipped contract tests entirely, wrote minimal unit tests, relied on manual QA. The pyramid became an ice cream cone, not because people didn't know better, but because they didn't have time. AI removes this friction. What used to take an afternoon, integration tests with containers covering happy paths, errors, edge cases, and timeout scenarios, now takes 90 seconds of conversation with an AI. The cost of doing it right dropped to near zero. There are 2 valid approaches. Approach 1, classic, TDD with AI. You describe the behavior, the AI writes the tests, you review the tests. This is critical because the tests are the specification. Then you ask the AI to implement code that makes the tests pass. Red, green, refactor, but at 10x speed. Approach 2, simultaneous generation. You describe the feature. The AI writes both code and tests in a single pass. You review both. Faster, but requires more careful review of test quality. In both cases, the code is disposable. The tests are the specification. If AI-generated code passes well-reviewed tests, you have confidence. If it doesn't, regenerate the code, not the tests. AI doesn't just make coding faster, it makes disciplined coding faster. Act 7, the honest caveats. Because no credible presentation about AI ignores the limitations. Caveat 1, the assumption echo chamber. If the AI misunderstands the requirement, it writes wrong code and wrong tests. Both pass, everything is green, everything is wrong. The human must still review what the tests actually check. Caveat 2, happy path bias. AI tests the happy path thoroughly, but undertests edge cases unless you specifically prompt for boundary conditions, error paths, and adversarial inputs. Caveat 3, over-mocking. AI loves mocking things because it makes tests pass easily. You must push back, use test containers instead of mocking the database. The AI won't make that architectural decision on its own. Caveat 4, coverage without confidence. AI-generated tests can produce high coverage numbers while asserting nothing meaningful. 100% coverage plus 0 meaningful assertions equals 0 confidence. Review test quality, not just metrics. Caveat 5, the human is still the architect. AI doesn't know which tests should gate PRs and which should run nightly. It doesn't know that payment processing is 10 times more important than profile settings. You provide the judgment, AI provides the labor. Bottom line, AI is the best testing intern you've ever had. Tireless, fast, capable. But like any intern, it needs direction, review, and architectural guidance. The senior engineer's job has been amplified, not eliminated. That's the end of part 1. In part 2, I'll show you exactly how I use Claude Code to build a full test suite across every layer. Unit, integration, contract, and E2E from scratch. In real time, subscribe so you don't miss it, and let me know in the comments which layer you want to see the most.